Hello, everyone, and welcome to Signals, Systems, and Signal Processing with Wolfram U. The topic of this lesson is continuous time convolution. As the title suggests, here we are going to discuss convolution, which is basically a mathematical operation, and it is denoted by an asterisk. For example, the convolution between two signals x of t and h of t is denoted as shown here. Convolution is very useful in signal processing. It relates the input and output of an important class of systems called LTI systems, or linear time-invariant systems. It is used to find the output of these systems for a given input signal if we know the impulse response of the system h of t. Assume we have an LTI system called S, as shown here, and we know its impulse response h of t. Now, if we have the input signal, any input signal x of t, then using the sampling property of the impulse function, we can express x of t in terms of a superposition of scaled and shifted impulse functions as shown here. So we know the output to the impulse function, or h of t, and we have written the input signal x of t as a superposition of impulse functions. Now, since the system is LTI, it is time invariant. So if the system response to delta t is h of t, then the output of delta t minus tau will be h of t minus tau. And because of linearity of the system, the output of x of t will be the linear combination of all these responses. So y of t, the output to x of t, is equal to the integration shown here. This formula is very powerful since it can be used for any input signal x of t. Let's focus more on this integration, which is called the convolution of x of t and h of t. It can be easily shown that the two integrals, as indicated here, are equivalent. In other words, convolution between two signals, in this case x of t and h of t, is commutative. Convolution also has the associative property, as shown here, and the distributive property, basically the convolution of a signal x of t with the sum of two signals h1 of t and h2 of t can be computed as the sum of the convolution of x of t with each of these signals. And the impulse function is the identity element for the operation. Convolving any signal with the impulse function returns that function itself. And convolving with a shifted impulse function shifts the function as shown here. Let's see an example to understand the concept of convolution and get more comfortable with it by visualizing the integration. For an LTI system that is modeled by the differential equation shown here, we want to find the sinusoidal response of the system, or the output signal when the input signal is sine of t and when the system is at rest, zero initial conditions. We want to visualize the superposition, the integration, through this example. Using the Wolfram language, we can solve the equation and find the output signal as shown here. Now, as mentioned earlier, using the sampling property of the impulse function, we can express sine of t in terms of a superposition of impulse functions shown in this plot. Remember, the impulse function can be thought of as the limit of rectangular functions as the width of the rectangle goes to 0. So we can decompose any signal x of t, such as this example, sine of t, as summation of a series of rectangles that you see here. When the width goes to 0, the approximation gets more accurate. Now, since the system is LTI, the output is the same summation of the output of the system to when the input is these rectangles. Using the Wolfram language, the output of each of these rectangles is the convolution of h of t, the impulse response, with these signals when the width is arbitrarily small. The shifted scaled version of the output signals can be plotted as shown here, and the summation can be plotted as you see here. And now if we compare this approximation, the output as this summation, to the actual sinusoidal response of the system that we obtained earlier, you can see that they are very close. This shows that the convolution integration works. Now that we know how the integration works, let's focus on the computation that is involved in this integral through another example. For the input signal and the impulse response shown here, we want to find the output signal y of t. We can use the Wolfram language to find the convolution. We can also plot the solution and see how the output y of t changes over time. Now, to find the convolution, notice that the integrand here is the product of these two terms. X of t minus tau as a function of the integration variable tau is the signal x of tau flipped with respect to the y-axis first and then shifted by t units of time, as you see here. Here you can find the plot of x of t minus tau and h of tau on the left side, and their product is shown in the middle graph. And the graph on the right-hand side shows the area of the product, or the convolution integral, which is in this example, the output response y of t. As we increase t, starting from negative infinity, the signal x of t minus tau slides from the left side of the graph to the right across h of tau. You can see their product shown in the middle is 0 at first, since the two signals do not overlap. And as soon as the front end of x of t minus tau reaches the point t equal to 0, and as it crosses over this point, we have non-zero values for the product, 1 times e to the power minus tau. And on the right-hand side, you see how the convolution or the system response y of t changes with t. So to apply this flip and slide method, we need to consider these two subregions separately, t less than 0 and t greater than or equal to 0. When t is less than 0, we have no overlap, the product is 0, and y of t is simply 0. For positive values of t, the integral of the product can be expressed as shown here. The integral is taken from 0 to the point t, and the result gives us y of t. As another example, let's convolve these two signals, x of t and h of t, as indicated here. Again, using the Wolfram language, we can compute the convolution, and plotting the results shows how the output signal changes over time. Now, to apply the divide and conquer approach of basically dividing the region of integration into non-overlapping subregions, let's plot h of tau and the time-reversed and shifted version of x of tau, x of t minus tau, to identify these subregions. Note that because of the commutative property of convolution, we can choose either x of tau or h of tau to flip and slide. Here we choose x of tau, the pulse signal, since it makes it easier to perform the operations. As we change t and slide the flipped signal x of t minus tau from left to right, for t less than 0, there is no overlap between the two signals, and the product is 0. As we pass t equal to 0, we have some overlap until we reach the point t equal to 3, and after this point, we have full overlap between the two signals. So for this convolution integration, we need to consider 3 regions. For t less than 0, the output is simply 0. For t between 0 and 3, the convolution is the integral shown here, taken from 0 to t, which can be computed using the Wolfram language. And for the interval t greater than or equal to 3, the convolution will be this value shown here. The output y of t for any value t will be given using this complete expression. In this lesson, we analyzed the convolution integral and showed how it could be used to find the output of an LTI system for any signal x of t, given that we have the system's impulse response. Through some visualizations, we saw how the convolution works and how it could be computed using a divide and conquer method.